Okay, we're going to continue on here, chapter 9. And last time we got into sort of solids and we talked about unit cells. And in terms of unit cells, there are a few different types. We have simple cubic, and simple cubic unit cells basically have one atom in it. And that one atom basically is in the corners of this cube. So in each of the corners, there's basically an eighth of an atom kind of sandwiched there. And we also have body center cubic, and that has two total atoms in there. This one also has basically an eighth of an atom in each of the corners. And this is the one that has one entire atom basically in the center. And then we have face-centered cubic, which actually has four atoms. And in this case, still the eighth of an atom in each of the corners. This one has kind of a half of atom cut in half, basically, on each of the faces. And since there's six faces, and you get a half for six, that's three atoms, plus the one in the corner gives you four. So depending on how these solids crystallize, maybe one of these few things, this allows us also, there's some differences in terms of the length. We could find the volume of a cube by taking the length cubed. And remember that each of these have a different sort of calculation used to calculate the length of the cell there, basically. So 2R for our simple cubic. And we have the square root of 4R divided by square root of 3 for our body centered. And then we have the last one there, which is our face centered, which is 2 times R square root of 2. So let's take a look at how we could use sort of this information here in a problem. So let's just say, for example, we want to calculate the density of aluminum if it crystallizes as a face-centered cubic cell. And in this particular case, that's an important piece of information, which is our face-centered. And what that will tell us is basically how many atoms we have in this case. And in this case, that's going to be 4 atoms. And again, that is the one that has a half atom on each of the faces and a whole atom in the corners. It has a radius of 143 picometers. Now, because this is face-centered to calculate the length of the cell, we do want to use the proper sort of formula there, and that is 2 times the radius times the square root of 2 in this particular case. So we want to calculate actually the density here in grams per cubic centimeters. So that is essentially what we want to try to figure out from the information given to us. So the first part that we can figure out pretty easily is the grams part. And that does come from, as I mentioned, what type of unit cell we're dealing with, which is our face-centered, and it has 4 atoms. So ultimately here, what we want to go from is atoms to grams. And we could do that first by using Avogadro's number. That's going to allow us to go from atoms to moles. And then we can use the molar mass to go from moles to grams. So here we would start with our 4 atoms. We will use Avogadro's number here, and that's going to go on the bottom, 6.022 times 10 to the 23 per mole. And that is going to cancel out the atoms. Obviously, these are atoms down here. And once we have that, that will get us 4 divided by 6.022 to the 23. It's going to give us something like 6.64 times 10 to the minus 24 moles. Now that we have moles, we can use the molar mass from the periodic table, and that's 2698 for aluminum. So we'll go 2698 grams per mole. Moles here will cancel, and this will give us our grams part. So we'll times that by 26.98. Gonna get us 1.7, we'll call it 9 times 10 to the minus 22 grams. There we go. So now we have the grams part. The next thing that we want to kind of figure out is the volume part. And remember, cubic centimeters is a volume. So we do know that volume is going to be length cubed. So that is what we're going to use really the radius here for. So get some room here maybe to write there. I lost my pen, so I'll try to write with my hand here. So we're going to take our length, which in this case is going to be 2 times our radius, the square root of 2. Now, what I'm going to do is, in this particular case, we ultimately want our sort of volume to be in centimeters cubed. Since our radius here is in picometers, I'm going to do a conversion first to convert the picometers into centimeters, and then I'll be kind of in the right units and not have to worry about it. So I'm going to do that first. I'm going to take 143 picometers, and pico is 10 to the minus 12. So in 1 picometer, there is 10 to the minus 12 meters. And there is 100 centimeters in 1 meter, right? So our meters cancel, our picometers cancel, and we will end up with here 143 times 10 to the minus 12 times 100 is going to get us here 1.43 times 10 to the minus 8 centimeters. And again, I'm just doing this to get it sort of in the right units. So now I could actually put that into here. So that's going to be 2 times my 1.43 times 10 to the minus 8 centimeters times the square root of 2. So let me pump that in there, times it by 2, times that by the square root of 2. And that is going to give us a length here of 4.04 times 10 to the minus 8 centimeters. Now, again, that is the length, and we do want the volume in this case. So the volume would be our length cubed. So we're going to take that number we just got, 4.04 times 10 to the minus 8 centimeters, and we're going to cube it there. And if we do that there, we will end up with 6.62 times 10 to the minus 23, and these are cubic centimeters. I get to do that. Now we actually have the bottom part here. So we have the grams that we calculated earlier. We have the, that's the grams right there. And we have the actual volume here. So to find the density here, we're going to divide those two. We're going to take both of those numbers there, which was 1.79 to the minus 22. So let me just do this on the next page, maybe, I think. So we will end up with here our mass that we calculated, which was 1.79 times 10 to the minus 22 grams, divided by our volume of 6.62 times 10 to the minus 23 cubic centimeters. And if you divide all that out, it's a long way to go to get to 2.71 grams per cubic centimeter, which would be our density here of our aluminum in this case. So when you're doing these type of problems, it's a very common problem, which is like calculate density. You use basically the type of unit cell to figure out how many atoms there is. You can use that to figure out the grams, and you will use the appropriate length calculation depending on the unit cell to figure out the length. You cube it because these are all cubes, and that will give you your volume. You just want to make sure, again, it's in the correct units. So I do find that just changing the radius into centimeters up front puts you in the right units, so you don't have to worry about doing it at the end, and everything will be in the right units. Any questions on that one there? All right, so why don't you try one here? That's the one we just did. So what is the density of rubidium if it crystallizes in a body-centered cubic unit cell with a radius of 247.5? RB is 85. All right, so let's take a look at this one. So again, some of the important pieces of information here is it's crystallizes on body-centered. So that's the one that has basically a atom in the corners and one whole atom in the middle. So that's going to have two atoms, which again is important information. Here we are still looking for our density in grams per cubic centimeter. So we basically just want to get both of those parts. So the two atoms is going to allow us basically to get to the grams. So we'll do our calculation here, our two atoms. We once again will use Avogadro's number, 6.022 times 10 to the 23 atoms per mole of rubidium. We could then use the molar mass from the periodic table to take us to grams, which is what we need, 8547 grams per mole here of RB. Moles cancel, atoms cancel, and that's going to get us here 2 times 8547 divided by 6.022 to the 23. It's going to get us a 2.8, looks like we'll go 4 times 10 to the minus 22 grams. So that is essentially the top part here, what we need. The bottom part, which is the volume, which is a cubic centimeter, is going to come from our radius here of 247.5. Once again, this is body centered, so it does have a different formula for the length. The length would be 4 times r divided by the square root of 3. And once again here, I'm going to do the conversion of picometers to centimeters just to get me into really the right units so everything's all good. So we'll go 247.5 picometers. Again, as we saw in the last example there, 1 picometer is 10 to the minus 12 meters. And then we could do our 1 meter is 100 centimeters there. And if we do that there, that's going to give us our radius, which is what this number is, times 10 to the minus 12 times 100. That's going to give us a radius of 2.48 times 10 to the minus 8 centimeters. And again, that's just going to set us up to be sort of in the right units here for our volume. Now we will put it now into our actual length equation here. So that's 4 times our radius, which we already converted into centimeters, divided by the square root there of 3. And that will then get us times 4 divided by the square root of 3. Looks like 5.72 times 10 to the minus 8 centimeters. So remember, this is not the volume, this is just the length. So because again, this is a cube, we can find the volume by taking the length now and cubing it. And since again, we already converted into centimeters, that means we will be in cubic centimeters, which is ultimately what we want. So we'll do 5.72 times 10 to the minus 8 centimeters cubed. Bad O there with my finger. And is that there? Maybe. There we go. So putting that in will get us we'll cube it there. 1.8, we'll call it 7 times 10 to the minus 22. And these are cubic centimeters. That is the bottom part of what we need. So now we're ready to calculate our density. So our density here will be our mass, which was 2.84 times 10 to the minus 22 grams, divided by 1.87 times 10 to the minus 22 cubic centimeters. And that's going to give us here a density for our metal of 1.52 grams per cubic centimeter. Any question on that calculation there? Yeah. It could be. So variation on these type of questions is they may perhaps give you the density and maybe has to work backwards to figure out like the radius or the length of the cell. So there are questions that you could kind of work backwards, but then you would be given some other information, like perhaps the density or something like that, and kind of work backwards. But I would say in most cases you'd be given the radius. Again, it may not always be in picometers, but it's a common sort of unit for it. But it is possible you could be given density and asked something like that, like, what's the radius or what's the edge length, kind of working backwards. Other questions? Okay. Question on these types of problems here. All right. That will essentially wrap up this chapter, I believe. Hopefully they got the same answer as we did. There we go. And there we go. All right, that's going to wrap up chapter 9. We're not going to worry about packing spears and stuff like that. So, all right. So in terms of this, you are responsible, obviously, for being able to do those type of calculations. You should definitely know the 3 types of cubic cells we talked about and how many atoms go with it. The formulas for the lengths will probably be given to you, but you do need to know how many atoms each one would represent. Okay. All right. And a lot of this chapter we've sort of covered previously when we were doing titrations and sort of concentration units and stuff like that. So that part of it, we're just going to kind of go over pretty quickly because we've kind of already done those examples previously and stuff like that. The main part of this chapter is going to be sort of the beginning and sort of the ending part, which is properties of solutions and colligative properties of solutions. So let's get into it. When we talk about solutions and we talk about liquids and liquids sort of mixing together, when 2 liquids completely mix together, they're said to be soluble in each other. And sometimes when we're talking about liquids and liquids sort of mixing, if they are soluble in each other, we sometimes refer to that as being miscible. And obviously here, if we had 2 liquids and we put them together, say in a test tube, it pretty much would all just look like one layer, basically, right? We wouldn't see any type of layers occurring and everything because everything would mix together. Now, when we have 2 liquids that do not really mix together and are insoluble in each other, that is what is known as being immiscible, sometimes referred to. And in that case, that you would definitely see some layering happening. So you'll see some different layers happening in the test tube, for example. And that's again because they are not going to mix together. So for example, if we took some carbon tetrachloride with some water, they do not mix together. And the real reason for that is it has to do with those intermolecular forces. So If you take something like carbon tetrachloride and just sketch it really quickly without all the non-bonding electrons, because I'm using my finger and not the stylus, which is somewhere, who knows. Here you'll get this geometry here that is symmetrical, and this is a non-polar molecule. As we know, water is a polar molecule. So this guy is polar. So when we get a polar and non-polar molecule together, they have really trouble interacting with one another because of the intermolecular forces. So as we know, as we talked about in the last chapter, water wants to roll with some hydrogen bonding. This non-polar molecule basically wants to use dispersion forces, and those are two very, very different types of intermolecular forces. And they cannot maintain that interaction over a long period of time. If you remember, dispersion forces are pretty much the main type of intermolecular force for nonpolar molecules, and it's the weakest of all the intermolecular forces, while hydrogen bonding is the strongest of all the intermolecular forces, and that's really what polar molecules use when they have the ability to hydrogen bond. So again, they just don't have that way of interacting over a long period of time together and maintaining that interaction. And that brings up a really important idea in terms of solubility. And that's the idea of basically like dissolves like. And what that means is if you're trying to mix things together, if you're mixing two things together that basically use the same intermolecular force that they use with themselves, they're going to have absolutely no problem interacting with each other. They're going to be really soluble in each other. If you try to mix together two things that use very different intermolecular forces, you're going to have a pretty big problem. So what that typically means is if you take, when we talk about like dissolves like, you will typically be good if you take something that's ionic and polar together. And that is because they could do ion dipole interaction that we talked about. So these guys can do some ion dipole interaction. That's all good, positive, negative attraction, good to go. If you take something that is polar and polar together, they're going to be good to go and going to be soluble as well because they're either going to use hydrogen bonding or they'll use dipole-dipole interaction. And that is going to allow them both to be really soluble in each other. Now, the one that sometimes people miss is if you take something that is nonpolar and mix it with something that is nonpolar, those guys will also be really soluble in each other because they're both rolling with dispersion forces. And again, they're both going to use the exact same type of forces with whoever's coming in as they do with themselves. So they're going to be really soluble. So this is the idea of like dissolves like. You're good to go if you got ionic and polar, polar and polar thing, non-polar and non-polar thing. You're only in trouble, bad news, if you cross over kind of polar and non-polar. Those things, as we just saw with the carbon tetrachloride and water, they're not going to be soluble in each other again because they are both using very different types of intermolecular forces. Any questions on that there? So when we talk about things that are soluble in water, ionic compounds are always soluble in water because when they go into water, they will break apart because they're strong electrolytes. And you basically get, as I just mentioned, you get that ion dipole interaction, which works really well. Again, when you get a positive ion, something like water, for example, can surround it through its negative side on the oxygen there. And again, that's essentially how we dissolve ionic compounds in water is basically all the water molecules surround all of the ions, and that allows it to dissolve, allows it to sort of disappear from our eyes. It looks like it's gone and went somewhere, and it's just not visible to us anymore because there's so many water molecules basically surrounding those ions. There's also non-ionic compounds that are soluble in water as well. Things like sugar and ethanol are soluble. Ethanol is something that looks like this here. It's really an organic compound. It is really an alcohol. And it looks something in this neighborhood here. And basically, water or ethanol here has two parts to it. And that is this part here, which is all the carbons and the hydrogens. And that essentially is the nonpolar part of ethanol. But what allows it to interact well with water is it has this front part here that is a polar bond, and it has that OH group, and that is our negative and positive that's happening here. And that OH group is a polar bond, and that is also a hydrogen that is directly attached to an oxygen, like a nitrogen or fluorine. So something like ethanol has the ability actually to hydrogen bond, and it can hydrogen bond with water because it has that bond, and it would actually hydrogen bond, for example, the negative side of water can interact with the hydrogen side there of that OH bond and do hydrogen bonding. And it makes something like ethanol really soluble in water because it has this little kind of polar bond on it. Even though it has a part that's nonpolar that can't really interact well with water, but because it has that little part, it makes it pretty soluble in water. Also, ethanol is not a tremendously large molecule, so it has no problem kind of interacting. I will say that it has that OH group, making it soluble and able to hydrogen bond. But for example, if you were to build out this sort of non-polar side to about 5 or more carbons with hydrogens and stuff like that attached to it. The solubility of that guy will then drop to almost nothing because it gets too big, and that big part that's non-polar kind of gets in the way of this OH part here, and it can't interact well with water. So sometimes referred to as steric hindrance is kind of the big non-polar part gets in the way. So even though it still has that OH bond, things with 6 or more carbons, 5, 6 or more carbons, it's just too large to interact with it. Now, sugar is a relatively good sized molecule, but one of the sort of added benefits that sugar has is, and we'll see a picture of it in a second, it pretty much is littered with OH groups all over it. So it has a lot of these OH groups all over a sugar molecule, and we know for sure sugar will dissolve in water. And everywhere there's an OH sort of group on sugar allows it to interact well with water, allows it to hydrogen bond with water, and it makes it very, very soluble. So although in the case of this like alcohol here, if you increase the nonpolar part, solubility goes down. But if you actually have compounds that have multiple OH groups on them, it allows them multiple places to interact with water and hydrogen bond with water, and typically will increase the solubility of something in water like that. Any questions on that there? And here's methanol, which again is a small alcohol. It has only one carbon. And again, the presence of this OH group going to allow it to hydrogen bond there with those water molecules and be soluble. There's our ethanol as well. Now, when we talk about something like oil and water, they don't mix. And as you might be aware of, when we have oil and water, like an oil spill, say in the ocean, the oil ends up basically just floating in the water. And that's because they can't really interact for a long period of time. And the reason for that is essentially oil is nothing more than a bunch of carbons, a lot of carbons, just imagine it keep going and keep going. And hydrogens basically. So just a bunch of carbons and hydrogens. And that is pretty much a nonpolar molecule all day. It's pretty nonpolar. And once again, here, oil is going to want to roll with dispersion forces. And again, our water, which is polar, is going to want to roll with hydrogen bonding. And for the long period of time, they will not be able to keep that interaction going. For a short period of time, as we might have talked about, like oil and vinegar salad dressing or something like that, you can mix it and it will mix, but ultimately it will separate apart from each other because it can't maintain that interaction. And that brings us basically to this idea of like dissolves like again. In addition, oil is really a super long molecule in a lot of cases of carbons and hydrogens. They actually break it up to make things like octane that we put in our cars and stuff like that. They crack them basically into smaller pieces, and you get like 8, like octane, and you have gas and stuff like that. So they take these really long oil molecules, petroleum molecules, break them up into smaller pieces, and you get different properties. But oil itself is a relatively large molecule, and when you are trying to get something to dissolve in water, you basically have water and water molecules hydrogen bonding with themselves, again, through the negative and positive side in these waters. So in order to get something to dissolve in there, you have to replace these sort of interactions with similar types of interactions. And when you get something like oil, which is not using the same intermolecular force and also pretty large, it just really doesn't mix really well. Again, it's like parking a car in a garage. A car will fit, right? SUV will fit, but maybe you come in with a semi truck, it's just not going to fit right into that garage, most likely, right? You get some of it in there, but it's not going to really pull in correctly. And that's sort of the idea here, is just too large. It's not using the right type of interaction, and it makes oil really insoluble with water. And typically, what we see is, the oil kind of floating on the water. That brings us to some types of interactions that we have on molecules. And as with the example of ethanol and methanol, there are certain parts to molecules that could be nonpolar, and there are parts that can also be polar as well. And that gives us 2 types of regions. One is known as hydrophilic. Hydrophilic means it likes water, so it's water loving. And those are typically any type of polar regions on the molecule. So in the case of ethanol, it's that OH group that gives it that polar sort of part to it. That is the part that really likes water. There's also parts that perhaps may not like water, and those are what are referred to as being hydrophobic, which means it's water hating. And in the case of ethanol, it's really the carbon and hydrogen part. So when you look at that ethanol molecule, this part of it here, which is all of our carbons and hydrogens, which is nonpolar, is definitely our hydrophobic part. This part over here, which is our polar part, is hydrophilic, and it likes that. So there's lots of compounds that have both parts to it. For example, I think we might see it in here, we might have talked about it in a previous chapter, but soap, for example, has a hydrophobic part and a hydrophilic part. Soap is really a long carbon chain, and we'll just call these squiggly lines carbons and hydrogens. And it also has this polar part. And this polar part is what's sometimes referred to as the polar head of soap. And this part here, which is basically all carbons and hydrogens, is the nonpolar tail. And this nonpolar part of soap is the part that likes dirt, because dirt is nonpolar, so it mixes well. And this is the part that, as you wash off your soap, you want water to mix with it to sort of wash off the soap. And that's the part that likes water in that particular case. And here again is what happens with our long chain hydrocarbons, which is an organic oil on the top, our water layer there on the bottom. This is actually octane, which is basically 8 of these carbons and hydrogens in a row. I won't draw them all because my finger is going to get tired. But basically 8 of these guys, repeated units. That's nonpolar. Carbon tetrachloride is nonpolar. So when we mix these 2 nonpolar liquids, you can see everything mixes in one layer. There's no layering happening. Obviously here, nonpolar and polar coming together with our water, we get different layers that occur because they're immiscible. The guy on the left there would be miscible in each other. Now, when we talk about solubility, when one substance does dissolve in another, usually the solute and the solvent, it is said to be soluble. So salt is soluble in water. When one substance doesn't dissolve, it's said to be insoluble. So oil is insoluble in water. There is a limit to how much you can get to dissolve, and it's based on temperature, especially when taking a solid in a liquid. It's based on temperature as to how much you could get to dissolve at that particular temperature. Typically, as we'll talk about, you can increase the temperature, and that usually will increase the solubility of a solid in a liquid. Gases are always soluble in one another, and when we talk about gases, gases are basically flying around. So just by that notion, they are constantly mixing with each other because they're flying around. So they are definitely mixing with each other. Some liquids are also mutually soluble in each other. So once again, polar and polar is going to be soluble, non-polar and non-polar is going to be soluble. And again, if you go polar and non-polar, insoluble when we look at those liquids. Molecules, again, with similar types of structure tend to make solutions, and especially if they're using the same type of intermolecular forces. A like dissolves like is that idea. Remember, again, I think we talked about a couple of places, but just a reminder that when we talk about solution, a solution has two parts, and that is, again, the solute, which is the smaller part of the solution, and the solvent, which is the larger part of the solution. And both of those together, when they do make a solution, those again are the guys that get the aqueous symbol next to it. So when you see that aqueous is a solution, it's a homogeneous mixture. It means everything's the same throughout, everything mixes. So the solubility of a solute in a solvent depends on temperature. Typically, the higher the temperature, the larger the solubility of a solid in a liquid. When you increase the temperature, you increase the energy that gets all that solid kind of moving, right, and creates more energy. Also allows in sort of the dissolving process a little bit more than things at kind of a lower temperature, not as much energy. They're going to want to kind of stay together. They don't have as much energy happening. At lower temperatures, we have a larger solubility of gases in a liquid. And that is, for example, here, we have a liquid dramatic drawing here. At a lower temperature, my gas molecule is going to be moving slower, which means it will stay in the liquid part for a lot longer period of time because it is moving slower, and thus they will be soluble in each other for a lot longer period of time. The solubility of gases depends on pressure. The higher the pressure, the lower the solubility. I'm sorry, the larger the solubility of gas. And that goes with our friend Boyle's law, right? As the pressure goes up, the volume goes down, and vice versa. As the pressure goes down, the volume goes up. So when we have really high pressure, we have a smaller volume. And clearly, if we have in a smaller volume our gas molecules, they are much closer to each other, so they're going to be mixing a lot more and going to be a lot more soluble in each other because of that smaller volume. Now, when we talk about solutions, there's a couple of ways that we can classify solutions. As I mentioned before, there is a limit to how much you can get to dissolve in it. When we get to a situation where we added too much solvent, that is what is sometimes referred to as a saturated solution. And a saturated solution is a solution where basically at that particular temperature, you've hit the maximum amount of solute that will dissolve in that solvent. So whatever solid you're trying to dissolve, you pretty much, if you've hit a saturated solution, you've hit the maximum amount that will dissolve at that temperature. That's sometimes referred to as the saturation point. You pretty much hit the maximum amount that you can dissolve. What that means is if you try to take more solid and dissolve it pretty much will not dissolve. It basically will just start piling up at that point, and you won't be able to do that. So, for example, if you get before that situation, so if you're before a saturated solution, you have basically what is known as an unsaturated solution. In an unsaturated solution, you haven't hit that point yet, which means if you want, you can continue to dissolve more solid. And you can continue to dissolve more solid in that solvent until you hit a saturated solution. So you can continue to dissolve until you hit that saturated solution, to which point there it will not dissolve anymore. Any questions on that there? Now, a third type of solution is what is known as a supersaturated solution. And really, one of the ways that you can make a supersaturated solution is making a solution really saturated at a higher temperature. So typically how you kind of make one of these is you take some solvent and you heat it up. And as you're heating up the solvent, that's going to increase the temperature, which means when you take your solid you want to dissolve in there, you're going to be able to dissolve a lot more solid than you could at room temperature because you're heating it up. So what you do is you kind of heat up the solution and then you pretty much just saturate the heck out of it, dissolve a bunch of solid in there at the higher temperature. It's not going to have any trouble dissolving because, again, you're increasing the temperature, going to allow a lot of that solid to dissolve. Then what you do is actually you kind of cool it back down and you leave it really untouched, very carefully. You just kind of don't touch it. Frankly, if you do this experiment, you don't look at it too closely because you don't want anything to happen. Now, you have this guy right now that is a solution, and we'll make it like that, and it's now cooled down. When it goes to cool down, the solubility of what you just dissolved in it goes down with it. It starts to decrease at the lower temperature, so you let it cool down. Now, what you have at this point is a solution. If you look at it, it's a liquid, it's a solution. And what you actually have is a pretty unstable solution at this point because you kind of cheated a little there. You heated it up to get a bunch of that solid to dissolve, and then you tricked it and let it cool back down without touching it. And now what you have is a solution that has way too much solid dissolved for it for like room temperature at this point as it cools back down. It is so unstable that if you take just like a speck, that whatever you dissolved in it, and you drop this one little speck of a crystal in there, it will go in and decide, no, that's no good. That will be way too much dissolved in here. And it will go from a liquid, and you could actually see the solid will start to come out of solution. And basically all of the solid will basically come right out of the solution. And you will be left with a rock hard solid at this point because basically just that little speck, you can barely see it, is enough to cause it to go, whoa, I should not have this dissolved in there. It is so unstable. I've done these demonstrations before that if you accidentally just kind of tap it on the bench without adding anything, it's enough to cause, that little tap is enough to cause all the solid basically to come out of solution. It's really, really unstable. Years ago, they used to let people do these type of experiments, but they had really bad instructions like put your thermometer in there. And then everybody had like lollipops because their thermometer got frozen into the solid as it comes out. And there's a lot of broken beakers and thermometers. So they decided maybe we don't do this experiment anymore. Here is that actual experiment. So this is an example of it. Sodium acetate. This is a supersaturated solution of sodium acetate here. And it's basically a solution, and you can barely see it, but right about there, just put like one little drop of it in. You can start to see the solid coming out of solution, more of it. And at this point, it's pretty much all rock hard at that point. It's kind of a cool little thing. You can actually just see it coming out. It's kind of like that one little piece, just enough to kind of push it over the edge. That'd probably be more, it'd probably be more like the expanding of water maybe in the freezer if they didn't put anything in it and they just like break the glass around the thing and it's just the ice that's in there. Is that what it is?
So
Yeah.
it's, sitting still in the freezer and it's brought to a temperature below its freezing point, and then it's touched just barely and it freezes really rapidly.
Yeah, I'm not 100% familiar with yeah, but it could have something to do with some of the colligative properties. So something like that, for example, we'll talk about later on in this chapter. You could actually lower the freezing point and things will freeze a lot quicker. So maybe it's something like that. Maybe they added something to it that might lower the freezing point and stuff like that. All right, so we could actually calculate the pressure on solubility of gases. An external pressure has the effect on the solubility of gases. This is what is sometimes referred to as Henry's law. It's the soda can sort of idea. And there's two types of formulas for Henry's law. C is equal to K times P. C is the concentration. So usually the molarity. S is the molar solubility. And that is also a fancy way of saying molarity, basically. So they're both molarity, whichever you want. K is Henry's law constant for the particular gas that you're dealing with. And P is the pressure in this case. And you can calculate how much pressure you might need. That happens, for example, like in a soda can, right? Here are some of the Henry's law constant for some different gases. In a soda can, right before you pop the soda can, you have a lot more of your CO2 dissolved in the liquid part. Because it's under pressure, all those CO2 guys are a lot more soluble in the liquid. Once you pop the top, right, on your soda can, you release the pressure, and that allows basically these gas molecules or CO2 molecules to be less soluble at that point. That's why if you look at a soda can, you sometimes see fizzing happening, right? Out the top. And that is your CO2 molecules escaping. Also, why if you leave an open soda can, right, and you come back to it a while later, it tastes pretty flat, right? And that's because air pushes the CO2 away, and you've now given the CO2 molecules an escape route, so your water is no longer carbonated. It's a little flat tasting if you taste the soda at that point. So we could calculate something like this. So for example, if we wanted to what is the pressure of CO2 required to keep the carbon dioxide at 0.12 molar in a soda at 25 degrees? So we could do this calculation. And again, we could use our formula of S is equal to K times P. And at this point, we're looking for the concentration of our CO2 to be 0.12 molar. We would go to that table there, for example, and look up the K value or Henry law constant for CO2, which is our bubbles in our soda, which is 3.4 times 10 to the minus 2 molar over atmospheres times our pressure. We're going to divide this guy to the other side, and that will get us 0.12 divided by 3.4 to the minus 2. That's going to give us like a pressure here of 3.53 atmospheres. As when we divide it, the molarity cancels, the atmospheres go to the top as you flip it over and divide. Normal atmospheric pressure is 1 atmosphere. So our soda can here is about 3 times our normal pressure, right, that we have going on there. Any questions on that calculation there? There we go. All right, so here's kind of the review part of the program here. We've talked about this, I think, in that chapter we did all concentrations and stuff. One of the concentrations we did talk about again is percent by mass or mass percent. And that again is the mass of the solute times divided by the mass of the solution times 100%. Remember on this one, as we talked about, it's really important, the bottom part here, and that is the mass of the solution. Whoops, come back. That is the mass of the solution. We want to make sure that you get both the solute and the solvent in that particular case, and not just the solvent. So remember that they sometimes will give you that sort of separate from each other. We also saw other percent concentrations. We talked about percent volume to volume, which is our volume of solute divided by the volume of solution times 100%. We also had percent mass to volume, which is our mass of the solute divided by the volume of solution times 100%. Remember that for the most part, the other ones you don't have to worry too much about in terms of the solution. It's really kind of that mass percent that they very commonly will give it to you, kind of broken up, the solute and the solvent. Remember as well that if you do have one of these percentages, you could use it as a conversion factor by assuming 100. So again, if you had your 4.0% by mass sodium chloride, that would mean that you have basically 4 grams of sodium chloride in 100 grams of solution, which you could use as a conversion factor like that, or you could also flip it around where the 100 grams of solution is on top and the 4 grams of sodium chloride's on the bottom. And you could do a similar type of one for any of these guys. It would just be more milliliters over milliliters and grams over milliliters in terms of the bottom one. All right. So we did some of these. Just a quick reminder here. We'll just go through this one pretty quickly. Our percent mass to mass here, we want the mass of our solute, which is our smaller part. So that is our 2.5 grams divided by the mass of our solution. So remember, we do need to add these together as this is our solute and this is our solvent. So that's going to give us 52.5 grams as the mass of the solution, not just 50, which is just the solvent. And I want to go with 13 point something, maybe not 4.76% by mass. Question on that one. Again, we did these examples in a previous lecture, and you can make sure you go back and look at it if you're not sure. Here again, if you have the percent by mass given to you, as I mentioned before, you could just turn that into a conversion factor. So that 37.2% by mass means that I have 37.2 grams of HCl in 100 grams of solution. Or again, I could flip it around and go in 100 grams of solution. I have 37.2 grams of HCl. So in this case, we have 35.5 grams of solution. Remember that as we talked about, that the name of the solution is the solute. So if I'm looking for HCl, then I'm looking for the mass of the solute in this case. So I could take my 35.5 grams of solution and just do a more dimensional analysis sort of calculation where I would use this as my conversion factor, 37.2 grams of HCl and 100 grams of solution. 100 grams of solution or grams of solution will cancel. Gets me 35.5 times 37.2 divided by 100. 13.2 grams of HCl in this case. Obviously, that is the same answer you would get if you just went into the equation for this and solve for the mass of the solute. Over here times 100%. So again, if you just went into the equation, it's basically the same calculation. You have all these numbers. You have this number, and obviously you have that number there. Questions on percent concentration. Again, we covered it a little bit earlier on. We also covered this guy as well. So just to review, this is obviously the chapter where it officially is in, and you still need to know it because you'll need to use some of these in some calculations later on. Molality, remember, is different than molarity. Again, molarity, which is our big M, is our moles per liter. Molality, which is our little m, is moles per kilogram of solvent. Remember that if you do need to go between these two units, density is kind of the thing that ties those two together, is the density. So in case you need to kind of go from one to the other, that's what you do. So this is moles of solute divided by kilograms of solvent. And again, this particular one, molality, is used a lot in colligative properties that we're going to talk about at the end of this chapter. And again, molarity a little bit will come into play, but definitely molality in these colligative properties is a concentration unit that's used a lot. So again, here, if we were going to calculate the molality of this particular guy here, the molality, here would be our moles per kilogram. So here we do need to find our moles, and we do have 61.7 grams. So we could use our molar mass like we've done before to convert this into moles. So we'll go to the periodic table there and calculate our molar mass. That is 3 carbons at 12.01 plus 8 hydrogens at 1.008 and 1 oxygen at 16. That's going to give us here 6009. So we'll go 6009 grams per mole from the periodic table. Going to give us our moles here of 1.0, I don't know, we'll call it 1.027. Now, in this case, we're not given the grams of water, which is our solvent, but we are given the density, and we do have the density of water. So we could use the density formula there to convert that into grams. So that's pretty straightforward. That is 1 gram per milliliter. Milliliters cancel. But remember that we don't want grams of our solvent, we want kilograms. So there are 1,000 grams in a kilogram. And that's going to get us to the proper units that we need. And again, that will be 175 divided by 1,000, basically. It's going to give us 0.175 kilograms for our solvent, which is water in this case. And now we have everything that we need to calculate the molality. So our molality here, 1.027 moles divided by 0.175 kilograms. Going to get us a molality of 5.87, we'll call it. Now, molality is much like molarity in terms of units. You can either leave the moles per kilogram, or you can just use the little m. So you can do either way there in terms of your answer. Question on molality. Like I said, you will definitely see molality here at the end of this chapter, as it's used in a lot of formulas that involve colligative properties. So, all right. We also talked, obviously, in a couple of chapters about mole fractions. So a reminder that the mole fraction, which is abbreviated with an X, also used in a couple of colligative property type of calculations. To calculate it there, we take the moles of what we're interested in, we'll call it A, divided by the total moles. Remember that this is not a percentage, so we don't multiply by 100. We just take the moles of what we're interested in divided by the total moles. It is sort of like a percentage without the multiplying by 100 part of it. And obviously here, as an example, we'll go back again through this one here that we did earlier. We could get our total moles by adding everybody up. So our total moles in this case is all these guys, 0.328 plus our 0.929 here. And that gets us 0.328 plus 0.929, 1.257 moles. And in this case, we're looking for the mole fraction of methyl alcohol, which was our first guy here. So the mole fraction of our methyl alcohol going to be the moles of the methyl alcohol divided by our total moles, 1.257. Once again, we're not going to multiply by 100 because we're not going to make it a percentage. And that gets us 0.2609, basically 26%, basically, is what that really means in that case. You could obviously do it for the other one, which would be 0.929 divided by the total moles are in this case. Since those are the only two, you could take 1 minus that first number and also get the mole fraction of the second one. We use 1 again because we're not multiplying by 100 to get a percentage, so we just use 1 as basically 100%. Question on mole fraction there. Yeah. The unit's actually just a number in this case. Again, it's not really a percentage because we're not multiplying it by it, but in reality, it is a percentage, just not actually multiplied by it. But we don't use percentages because we're not multiplying by it. So really, no unit, just kind of like a point something type number usually. Other question? Yeah.
Would you want us to just write units at the end, or?
No, this would be fine for mole fraction. Again, technically speaking, the moles on top and moles on the bottom cancel, so there really is no units left at that point. It's really just a number. Um, and again, since we're not multiplying by 100 to turn it into a percentage, it's not a percentage either, really. So you could just leave it as a number in this case. Yeah. Other questions? Yeah. And obviously, we can't forget our most important concentration unit, which is our friend molarity. And molarity is big M, which as we know is moles divided by liters. It really is moles of solute divided by liters of solution. Remember, as we've seen, we can use any of these three things. So if we want liters, that's going to be moles divided by molarity. And if we want moles, that's going to be liters times molarity. Remember that if you do have something in molarity, like for molar sodium chloride, and you're going to do some type of calculation, as we talked about, it's a really good idea to get rid of the big M and use both units there. The number stays with the moles, and it's always 1 liter of sodium chloride. Once again, that just visually allows you to see both units. It also allows you to do more of a dimensional analysis calculation. And more importantly, hopefully it will allow you not to screw up the calculation because, as I mentioned before previously, super common. People leave the big M and all they think about is moles, have no idea again about the volume part of it. So if you put both of those units in there, do it for as a dimensional analysis sort of calculation, it will actually do, for example, the rearranging of these equations for you. If you just kind of do opposites cancel in terms of the units, you know, to worry about. Also, a reminder that you definitely, if you're using molarity by itself in volume, the volume should be in liters so that you end up with moles. Reminder that you can definitely multiply milliliters times molarity. You do not get moles, you do get millimoles, which if you're thinking and you're getting moles, you're going to be about 1,000-fold off from the correct answer in that case. So you could absolutely do milliliters times molarity, but you do not get moles, you get millimoles. I would say probably 9 times out of 10 or even more than that, you're looking for moles if you're doing that calculation. So just make sure that it is in liters when you use it with molarity so everything cancels out correctly. All right, any questions on that there? All right, we're going to take a break here at this point.